You've probably heard of the 80-20 rule, especially if you're a crime analyst or a student who's learning the fundamentals of crime mapping using GIS. The basic idea is simple. In many systems, a small share of causes tends to account for a large share of outcomes. That idea is usually traced back to the Italian economist Vilfredo Pareto, who noticed that a relatively small proportion of people in Italy owned a large proportion of the land. Over time, that basic insight showed up in sociology, healthcare, and policy analysis, not because the numbers are exact, but because the pattern keeps repeating. In crime analysis, that often means a small share of places account for a disproportionate amount of crime. What's useful about learning the 80-20 rule isn't the exact numbers it produces, it's the way it forces us to think more strategically about place. Instead of asking, where is crime happening, the 80-20 approach asks, where does crime concentrate? And just as important, how concentrated is it? That distinction matters for patrol allocation, problem-oriented policing, and even place-based intervention efforts, especially when we pair it with other tools like co-location analysis. If you can identify the small number of locations driving a large share of incidents, you're in a better position to make decisions about how those clusters might be broken up. In this tutorial, we'll walk through how the 80-20 tool works in ArcGIS Pro, how to set it up a few different ways depending on your goals, and how to interpret the outcome it produces. To get started, I created a project in ArcGIS Pro, and I brought into it a year's worth of violent crime incidents for the city of Philadelphia, as well as the city limits for Philadelphia, mostly as a reference polygon. But I also brought into it the police service areas, and I'll deactivate crime to show you what this looks like. The police service areas in Philadelphia are the 66 patrol areas for the city. These are the local beat areas into which patrol officer activities are largely constrained. And in addition to the police service areas, I brought in a tessellation I created with 800 by 800 foot grids. And there are 6,520 of these grids. The importance of the police service areas and tessellation will become more intuitive as we move forward. In the meantime, I do want to take a quick look at the attribute table for the violent crimes. We can see that over a 1-year period, there were 40,644 violent crimes across the city. And again, they looked kind of like this. They are not evenly distributed, but they are vastly located. The violent crimes include aggravated assault, criminal homicide, robbery, rape, and other assaults with and without firearms. So we're interested in understanding how crime might cluster across the city in a way that is useful for criminologists and crime analysts. That is looking at that 80-20 distribution. So to get there, and the first thing we're going to do is come up under geoprocessing, type in 80-20, and click on the tool itself. Our input will be the violent crimes. We are going to use the cluster method when it comes to aggregation. The 80-20 tool gives you two different ways to aggregate events, and the choice you make here has analytical consequences. The cluster method works entirely with points. The tool groups nearby incidents together based on spatial proximity without reference to any predefined boundaries. What you get are clusters that emerge from the data themselves, essentially answering the question, where do events naturally concentrate in space? And our cluster tolerance is going to be 500 feet. You can specify any distance or cluster tolerance for the tool, and it will create an 80-20 output, follows your input parameters. In our case, we're trying to best honor, in a way, what constitutes place. It's true that Philadelphia itself is quite a large city geographically, but people who live in any city tend to live in their neighborhoods and on their street blocks. In Philadelphia, the average street block is around 400 feet, Police departments often use 500 feet as their operational linear units. So in our case, when we specify our cluster tolerance, we're going to look at crimes that are clustered within 500 feet of each other, and that's how the tool will create its clusters. So once we specify that 500 feet, we can click Run. Okay, this is the output that the tool generated for us. And if you look over here in the symbology, you'll see that the symbols are a series of proportional dots. The largest one contains 36,632 crimes of our 40,000 crimes. So that's a very large cluster. The second cluster contains between 18,000 and 27,475 crimes on down. And you'll notice here where it says these gray points fall outside of the top 20% of locations. And this is just a way for the tool to simplify the visualization. So let's open the attribute table and see what this really means. The tool identified 245 separate violent crime clusters. That means 245 of these clusters where there were enough violent crimes that were within 500 feet of each other to become a cluster. But this top one in the first row, this is kind of a supercluster. It contains 36,632 violent crimes. And when we look across these other three rows, incident, cumulative incident, and cumulative location percentages, we get a clearer picture of how this clustering is playing out. 93.54% of all the violent crimes are in this cluster, and that cluster accounts for 0.41% of all the geography of the crime clusters. So that's not 0.41% of the geography of Philadelphia. It's 0.41% of the geography of the 245 clusters. And as you might infer, this is a huge cluster with a very large number of crimes. In fact, violent crime in Philadelphia, according to this analysis, is far more clustered than a standard 80-20 rule would otherwise imply. This large green point does not by itself represent 36,000 crimes. In other words, 36,000 crimes are not packed into the geography within this large green point. This green point is the centroid, or the central location of a very large cluster of violent crimes. So if we activate the violent crime incidents, we can kind of see what that means. This cluster is very large, and it's a connected cluster. So at the very least, it's likely that the crimes are clustered within this large perimeter, and perhaps even larger. And it would be up to the analyst to figure out exactly what that clustering means. And because of the extreme clustering pattern here in Philadelphia, it makes sense to run a couple of other 80-20 analyses using slightly different parameters. So if we come up under geoprocessing again and click on the 80-20 tool, we're going to input the violent crimes again. Only this time we're going to switch from the cluster aggregation method to the closest feature. And here is where the police service areas come into play. When I use the closest feature method with police service areas, I'm aligning the analysis with how the police department actually operates. These polygons are irregular in shape and size, which is a reflection of staffing patterns, call volume expectations, and supervisory structure. The 80-20 results here tell us which service areas account for a disproportionate share of crime as the organization experiences it. The trade-off is that differences in polygon size can matter. Larger areas have more opportunity to accumulate crime incidents, so the results mix spatial concentration with operational geography. We're essentially going to tell the tool to bin all of the violent crimes into their encompassing police service areas, and then conduct an 80-20 analysis within the context of how those crimes are clustered within each of the police service areas. So once we set this up, we click on Run, and we see that the tool creates a new feature class layer using the police service areas as the unit of spatial aggregation. The top category of PSA clustering contains between 1,370 and 1,538 violent crimes. And that's this one right here. So that would be 1,538. The PSA with the next level of clustering is actually where our green dot is from the previous analysis, and that contains somewhere between 1,202 and 1,369 violent crimes. Opening the attribute table, we see the incident count and the percentages across the top. So if we scroll down, we want to come and look at this cumulative incident percent, and we want to scroll down until we get to 80. So that's this row right here. When we look at the cumulative incident and cumulative location percentage columns, roughly 81% of all the violent crimes are clustered into 62% of the police service areas. This is a little smoother than the previous analysis. It's not quite as clustered. It's a little bit more even. And that doesn't surprise me, given that we are snapping these crimes to their relevant police service areas and looking at them not in relation to all other crimes around the cities, but only within their own PSAs. So we would expect to see different clustering dynamics within these PSAs. It's important to note that the PSA is the unit of operation for a police department. So this is interesting and useful for a police department to understand, perhaps even more so than the first analysis that used the straight point clustering method. I will say, though, because PSAs are so different in size, it makes it hard to really comprehend how the size itself isn't creating an artifact for the clustering. Let me show you what I mean by that. If we click out of here, we have one more 80/20 analysis to conduct. So we'll go under geoprocessing one more time, click on 80/20, and the input is going to be the violent crime. We're going to switch to closest feature, and this time we're going to use the tessellation as our comparison feature. Once we set that up, we click Run, and as before, we've created a new feature class layer. If we scroll in, we can get a better sense of what's happening here. Now remember, these tessellation grids are 800 by 800 feet, meaning that the tool essentially placed all the violent crimes into their encompassing grids and conducted the clustering analysis within each of these grids. So here, we're being very sensitive to the geography of place. The crime clusters get to vary every 800 feet, but it's not quite as organic or independent as just a point clustering analysis. And using tessellations, it's not exactly operational for police departments, but they can get a better sense sometimes of what the clustering looks like when they cluster into smaller locations that are uniform in size. So if we open up the attribute table, we see that, again, this tessellation contains 6,520 equal-sized grids. We have the same fields going across. So we're going to scroll down again to get to 80% on the cumulative incident percentage. And we arrive here at row 1642. We see 80% of all the violent crimes are clustered into 25% of the tessellation grids. That's the closest we've seen to a standard Pareto distribution that assumes the 80/20 dispersion. If we click out of the attribute table and reactivate the violent crimes, we see that for the most part, violent crimes follow pretty well what the tessellation looks like in terms of two-dimensional distribution. But we can see in these areas where the grids are particularly dark that these are areas where the crimes are going to be closest together. And that's the 80/20 tool in ArcGIS Pro. What I wanted to show you here isn't a single result, but how crime concentration changes as we change how we define space. Using the cluster method, concentration looked extreme. At a 500-foot tolerance, violent crime formed one very large cluster, accounting for 93% of all incidents. That tells us a lot about spatial connections, but it's not very operational. Switching to the closest feature method with police service areas moved the analysis into an operational frame. Concentration appeared weaker, not because crime is less concentrated, but because incidents are being aggregated to large, irregular units. Finally, using an equal-sized tessellation produced a clearer Pareto-style pattern with a relatively small share of grid cells accounting for a large share of violent crime. That happened because unit size was held constant, making concentration easier to compare. For police departments, this kind of sequencing is useful. Clustering shows how crime connects across space. Operational units align analysis with deployment, and tessellations provide a standardized way to assess concentration. The takeaway isn't whether crime follows an exact 80-20 split, it's how your definition of place shapes what concentrations look like. Once you understand that, the tool becomes much more powerful. Thanks for watching. I'll see you in the next one.